So we're shifting gears away from pure theory and getting now into experimental data. So we're going to be focusing on vibrational motion first. And then in the middle of this vibrational motion, we'll insert rotational motion and then look at vibration and rotation combined. Because we have two labs that are coming up. Next week is going to be the vibrational analysis lab, where we compare benzene and chlorobenzene. And benzene obviously is a very symmetric molecule. What's the point group of benzene? D6H, right. And that H, that D6H, that means it has an inversion center. And so if a molecule has an inversion center, then the IR modes and the Raman modes are mutually exclusive. Like a certain vibration will be Raman active but not IR active, and a different vibration will be IR active and not Raman active. And so how many atoms does benzene have? 12, okay. What about chlorobenzene? Also 12. We just took off a hydrogen and put a chlorine on there. But what's the point group for chlorobenzene? C2V. And all the IR and Raman modes are active. So in both spectra. So for a C2V molecule, we see the result of broken symmetry. And so that's what we're going to be looking at next week. Now the spreadsheet work that we're going to be doing, we're going to get the raw data from the spectrometer and we're going to plot them on top of each other. So some of the skills that you'll learn will be plotting multiple spectra on a graph. So we'll have a stacked plot of, say, benzene, and you'll have the infrared and the Raman, and then the Gaussian simulated and the Raman simulated, all for benzene. So there's 4 spectra on one plot. And that's going to be the most useful skill that you'll have in going forward in preparing lab reports for other classes and also doing your undergraduate research. So this idea of being able to plot multiple spectra on one graph is a definite skill that you'll have. I had a student that was kind of funny. He didn't go into science. He actually started working at, gosh, I think it was at an airport. But he walked into his manager's office and his manager said, "I need to plot this data, but I don't know how to use Excel. Do you know how to use Excel?" And he said, "Yes, I do." So he plotted the data, labeled his axes, made a really nice graph and gave it to his boss. And his boss looked at it immediately and said, "I'm not paying you enough. You're going to get a raise." Now, why would a boss do that? I mean, he's already accepted a lower paying job. It's called competition. He knows if this employee can do this, he's going to be marketable to other people and he wants to keep him around. Okay, so that was pretty cool. So the skills he learned in this class in Excel got him a raise on the spot. So that's nice. Let's hope that keeps happening. Okay, so vibrational spectroscopy. We're dealing with vibrational motion in a molecule. And we use the basic physics model, the harmonic oscillator. So in developing quantum mechanics, this was one of the simplest approximations. Take hydrochloric acid, or HCl. You have this really heavy chlorine. You have this tiny little hydrogen moving back and forth on that molecule. It looks like a mass on a spring. And so let's treat it with the simplest physics model. Let's put the potential energy of a harmonic oscillator, and that's the equation for the potential energy. And you can see that K, force constant, would be in newtons per meter. How much force does it take to stretch that bond a meter? Of course, you can't stretch a atom's bond, a molecule's bond 1 meter, but that's the units for force constant is newtons per meter. And then it gives you this parabolic potential energy surface. So this right here is the harmonic oscillator potential energy, this blue parabola. Okay, so V would be plotted right there. The black curve is more related to the reality of a stretching bond. Okay, so a bond, if you pull on it long enough, it's going to break. And as you pull on it, the force gets a little easier than it would be for the harmonic oscillator. Notice the harmonic oscillator will not dissociate. The potential energy surface goes to infinity. Okay. Now, polyatomic vibrations are determined by the projection operator, which it's available in your notes. It was a supplemental set of notes. We'll go through the projection operator in detail when we get to molecular orbital theory. But essentially, you take the character table and you project that motion through the different rows of the character table, and you build up what happens to the different arrows. And that's where those arrow diagrams that we've been drawing for water and so on come from. They come from this projection operator and a character table. Because you're using the character table, these vibrations have a known symmetry. So like if you do water and you run it through the character table, you're going to know that that vibration is the B1 vibration or the B2 vibration or the A1 vibration. And you're going to know by looking at all of the possible motions in water that you can't have an A2 vibration because there's no motion in the molecule that will stay on that row of the character table. So using the character table allows us to get these normal modes of vibration. So that's a vocabulary word that you'll hear me say all the time, normal modes of vibration. And you know, because I've tested you on it twice now, how many there are in a molecule. How many normal modes of vibration are there in a molecule? 3n minus 6 if it's nonlinear. And if it's linear, 3n minus 5. Right. And so let's look down here at the very bottom of our potential energy surface. So let's zoom in on that spot. And here we have our harmonic oscillator potential, and we have the first 5 wave functions for vibration. So these wave functions look similar to our particle in a box, but they're not the same. In the particle in a box, we had sines and cosines. This is a Gaussian function down at the bottom. So once again, we see this normal distribution, only it's not a line shape, it's actually the vibrational wave function for harmonic oscillation. Okay. And so then what's the next one? It's also a Gaussian, but multiplied by a polynomial. So we have in front of our wave function this polynomial called the Hermite polynomials times the Gaussian function, and it gives us this increasing oscillation, higher curvature, which means higher energy. And so these are our vibrational wave functions. There's one important feature. In the particle in a box, we did not have equal energy spacing. Right? The energy went up as quantum number squared. So as n went up, then it was the square of n that caused the energy to jump, because energy was equal to n squared times a squared over 8ml squared. But in the vibrational motion, we have a totally different energy equation and different wave functions. And so we have a new energy equation that you need to commit to memory, and that's this down at the bottom. E equals hc nu tilde, which is the frequency and wave numbers, times the vibrational quantum number, v plus 1/2. It may be a little small to see in the back, so I'll write it really big on the board. So this is the vibrational frequency. That's the Greek character nu. And this is the quantum number v. And they look very similar on the screen with the fonts that Windows uses. Okay. But by context, you should be able to figure it out. The thing that's in the parentheses with the 1/2 is the quantum number, v plus 1/2. Okay. And the thing out front with the tilde, that's the vibrational frequency, Greek character nu. The tilde indicates that it's in wave numbers. And we'll look in a minute how those units all work out to give you energy in joules. Okay. Now, notice that the ground state is v equals 0 in vibrational motion. So it's 8 in the morning, everybody wake up. This is not, v equals 1 is not the ground state. V equals 0 is the ground state. Whereas in a particle in a box, the ground state was n equals 1. So that's a substantial difference. So what does that mean for the fundamental? The fundamental is 0 to 1. Whereas in a particle in a box, the fundamental was 1 to 2. Okay. So these are things that you've memorized, but now we need to modify slightly because we have a different system. We have vibrational motion now, not just a particle in a box. Okay. And so then the next level is 1 and 2 and so on. So they're sequentially numbered, starting at 0, going to infinity in theory, but they don't ever go to infinity. They just go to large numbers. Okay. So that's the quantum numbers. That's the energy equation. Let's look over here about the symmetry of the wave function. Notice it's centered on 0. And so we ought to be able to come through and just recognize. Yeah, so you see here the left and the right are the same, so that's even. The left and the right are opposite, that's odd. The next one, even. You see the left and right are the same. The next one, the left and right are opposite, so that's odd. So we have the same kind of thing we have in the particle in a box, the same behavior of even, odd, alternating all the way up. Yes?
So particle in a box, evens are odd and odds are even. In vibrations, odds are odd.
Yeah, which, again, it's a confusing statement because of the equivocation. Odd numbers, like the quantum numbers, are odd symmetry. But I don't like to do that because it sounds ridiculously confusing. Yes, because especially the particle in a box, that one where it was really a mess. So let's just focus on even vibrational functions or even wave functions correspond with even quantum numbers. So you put those two descriptors in there and then you can use that statement. Now light is still odd. We haven't changed that at all. And light will be associated with one of the x-axes or y or z-axes, one of the Cartesian coordinates. And so here we have an even level going to an even level with odd light. So you should be able to put that transition dipole moment integral together and see that that would not be allowed. Okay, because we have even times odd gives odd. So let me just look at that. So this piece gives odd, and then this piece here, even times that odd gives odd. And so the integral over all space of an odd function is equal to 0. But at going to adjacent levels, so going from an even level to an odd level with light would be allowed. So that integral would be non-zero. And so already we can look at this and say, all right, with our selection rules, we should have the same kind of selection rules of delta V equals 1, 3, 5, 7, 9. Now, there can be a situation where instead of an odd function here, instead of these being odd, and this was the example on the previous exam where it was A1, 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 A1 all the way up. Because the vibrational motion for both of the or let's see, was that a water problem? Yeah, water. So it was an A1 motion because it was the symmetric stretch. And so the odd nature of both of those masses, the hydrogens stretching away from the oxygen, canceled each other out so that the overall motion was even. So it was even all the way up. And so there your selection rules completely open up. For Z-polarized light, every transition was allowed. 0 to 1, 0 to 2, 0 to 3, 0 to 4. So now let's look at this part of the curve. We've looked down at the bottom. Now let's look up here where the harmonic oscillator model and the more realistic model, the dissociative model or anharmonic model, diverge from each other. So here we have the energy levels pasted onto the anharmonic potential. And so all we do is we started with the harmonic oscillator, which has the same bond length all the way up, but we realized that's not what happens in nature. Bonds actually stretch and eventually dissociate. So the anharmonic oscillator, so all we've done is said we know the harmonic, now we have not harmonic. So this is the anharmonic potential. So putting the A in front of it negates the harmonic part. And so this is decreasing energy spacing of the energy levels. Now you tell me, using your thinking, so do this by analogy. You know what happens when the box increases with the particle in a box, don't you? The energy levels get closer together. Can you see how that gives you some intuition as to what happens with anharmonicity? Harmonic oscillator, the box is increasing, okay, and the energy levels are equally spaced, but what if one side really stretches away? Notice how as I go up, that box this box size is increasing dramatically and the energy levels get closer and closer together. So just understanding how the harmonic oscillator behaves, the particle in a box behaves with increasing box length, you can understand why the energy levels get closer together with the anharmonic potential. That box is increasing dramatically. The harmonic oscillator is just the perfect stretch of the box so that the energy levels are equally spaced. If it was vertical walls, you'd have the particle in a box. If it was a parabola, you'd have equally spaced energy levels. But if it's bigger than a parabola, then the levels get closer together. And that's what we see in the anharmonic potential. That means that the bond length also stretches. So as you excite a vibration, the atoms spend more time apart. Their average bond length is longer. And we can see that spectroscopically. In fact, for the carbon monoxide molecule, as it spins and vibrates, the bond stretches. That's called centrifugal distortion. So as the molecule spins, it's like it's in a centrifuge, and the atoms spend a little bit more time further apart. It actually stretches the bond. And then these down here are the dissociation energies. Now use this plot to understand the difference between the subscript E and the subscript 0. So these are not even an odd now. This is E for equilibrium and 0 for the 0th vibrational state. You see where they originate? DE originates down at the bottom of the potential well. And that's also RE, that's the bond length at the minimum of that potential well. So that E stands for equilibrium. So the equilibrium bond length, and it's unfortunate, I don't know what else to call it, but it's really, it has nothing to do with chemical equilibrium or thermal equilibrium. It just means it's the minimum of that potential energy surface. So we just call it the equilibrium bond length. Yes?
Isn't this just like an upside down Gaussian?
No, it's not. Yeah. Which one are you talking about?
The anharmonic one?
It's actually not, because it's not symmetric.
Okay.
Yeah, so a Gaussian would be symmetric.
So the other side wouldn't be the same as this one? Or?
No, because we're looking at internuclear distance. And so I've kind of broken one of my own rules. Whenever you show a plot, look at the axes first. So the y-axis is potential energy for the molecule, and the x-axis is internuclear distance. So think about this as like an HCl molecule. Okay, so let me draw down here at the bottom. We might have at 0 internuclear distance the location of the chlorine atom. And then stretch some distance away is a hydrogen, not to scale. Okay. And so this thing is vibrating back and forth inside that potential. And so as it stretches, it's able to stretch further than it is to compress that bond. Because as the bond gets shorter and shorter, the nuclei start to see each other. And the repulsion of those nuclei is really strong. So that's why the potential is steeper than the harmonic oscillator at close distances, and it's more gradual than the harmonic oscillator at long distances. So you can deform the spring if you stretch it too much. Yes?
So make sure I understand your plot. So are we saying that Cl isn't moving?
Because it's about 35 or 37, depending upon which isotope, and hydrogen is 1. Yeah.
So because of the mass difference, we can start 0 at Cl and act like it's not moving.
Exactly. Yeah. Yeah. And you can test that by calculating the reduced mass, which we'll talk about in a little bit. And the reduced mass is pretty much like a hydrogen atom. So the thing that's moving is the reduced mass. And the reduced mass for HCl is mostly the hydrogen mass. Yeah. But the dissociation energies, you get a slightly different number if you calculate it from the minimum of the potential to the bond dissociation limit, or versus V equals 0. And so just wanted to highlight that those subscripts mean something. RE and R0. RE would be the equilibrium bond length, the minimum of that potential. R0 would be the ground state vibration, the ground state bond length. What about R1? R1 would be the V equals 1 bond length. R2 would be the V equals 2 bond length. So here's a sort of a survey of all of the equations. We've seen the energy equation. Here's the harmonic oscillator frequency equation. So this is how the frequency depends upon that force constant and the reduced mass. So K is the force constant in newtons per meter. C is the speed of light, as you well know. And then mu is the reduced mass. And so this is, for a diatomic molecule, this is the equation for reduced mass. Now, for your lab, you want to use accurate masses. So you would want to go to the CRC or the NIST webbook and look up the isotopic masses. there is no such thing as a chlorine atom that weighs 35.5. Okay, you look up here, you see chlorine's mass, 35.4527. There's no chlorine in nature that weighs that. You have chlorine 35 isotope and chlorine 37 isotope. And when we're doing spectroscopy on actual molecules. And so you would see a peak for the 37 isotope and a different peak for the 35 isotope. And so in your lab, you would want to use, for carbon monoxide is the one we're going to do, you would want to use the isotopic mass, carbon 12 and oxygen 16. So, so the 12.01, not good. Okay, it's going to give you a wrong value. You need to go in and use carbon 12, actually just defined carbon 12 with, you know, since it's defined, essentially it has an infinite number of zeros behind it. But oxygen 16 is not good enough, at 15.99 and so on. You go find the actual isotopic mass for oxygen 16 and use that in your lab. But in the tests and in your homeworks, like chlorine 35 weighs 35. Okay, chlorine 37 weighs 37. So just use the isotopic number. Carbon 13 would be 13. Deuterium would be 2. Hydrogen would be 1. Okay, that's good enough for hand calculations. So does everybody understand the difference? If you're going to go and use Excel, Excel doesn't care if you have 16 decimal places. Okay, but in the test, don't use 16 decimal places. Okay, you're going to screw that up, and it's just going to make me, you know, scratch my head. So that'll be good. And so then, you know, if you're looking at excited states and dramatic situations where you've got really large vibrational excitation, we'll do this in the iodine lab. We have really heavy atoms and they get excited in the upper excited vibrational states. You need to take into account anharmonicity. And these are the higher order terms. So this is a great example of what scientists do. They start with the sort of the base model, the harmonic oscillator, and they want to adjust it a little bit. They don't worry necessarily about what nature actually does. They just put in higher order terms. It's a polynomial is what it is. Look at this equation, and can you see the polynomial? If a linear model doesn't work, you add a quadratic term. If a quadratic model doesn't work, you add a cubic term and maybe a quartic term. And so you can see that the energy is linear in quantum number, and so we adjust that because it's too high, right? We want to decrease those energy levels, so we subtract a quadratic term. So we have Hc nu. We add in an anharmonicity constant, which we don't know. We just fit it to the energy levels, and that fit depends upon the quantum number squared. So this is just the higher order term. It's just an x squared term with a constant out front that we fit to nature. And then that subtracts too much, and so then we add a little bit back with the cubic term. And if we could have enough data on all of those energy levels, we might add a quartic term. And I guess it would be z, because we have an xe and ye, maybe a ze with the x to the fourth or b to the fourth.
So only the squared term will ever be subtracted?
Yes, and then the cubic term would be added. Yeah. So this, you know, that x term, the second order term, adjusts it for a little bit, but then because it's negative, the energy levels get too close together and they don't match nature. And so then we add back a term that depends upon the cube of the quantum number. So then it really is only effective at higher quantum numbers, and so then it adjusts it a little bit more.
So will they ever just like keep going larger and larger? Like
I've never seen anything beyond y. And so for diatomic molecules, we have the most data, and you can go and see in their tables what the experimental results are for xe and ye. We will determine the xe constant for iodine. So the last lab, the iodine lab, we will fit the spectra of iodine, and we will actually solve for the anharmonicity constants in the ground state and in the excited state. Yeah. Now here are some molecular constants for diatomics. It's kind of an eye chart. I don't think you can see it, but this is a great table for you to practice on. So in the homework, I have a couple of problems. I took the vibrational frequency for HCl out of this table, and the rotational constant for HCl out of this table, and the bond length. And so this is a good set of data. You can practice going from vibrational frequency to force constant, or from force constant to vibrational frequency using the reduced mass. And you can use this thing called the rotational constant. This will be important in our next lab, the rho vibrational spectrum. And so here's the equation for the rotational constant. And then this stuff down below are the unit analysis. So I have force constant, reduced mass, C. How does that end up in inverse centimeters? Well, K is in newtons per meter. This is a newton here, and this is a per meter. And then the reduced mass is in kilograms. So the kilograms cancel. The meter cancels this meter. I end up with the square root of 1 over second squared. So I end up with 1 over seconds on the top and 1 over seconds on the bottom. And so that's going to cancel. And I'm left with inverse centimeters. So this is a great way for you to make sure you understand what are the units that you're going to use for reduced mass. If you come up to the periodic table and you just grab grams per mole and try to throw that into this equation for the reduced mass, you know, it's not going to work. Okay, you need kilograms to work with newtons. So this gives you an idea of what kind of units need to be used. And it's almost always about the units. When you're trying to do a problem and it just won't work out, it's probably because you're not paying attention to what units you need. Let's look at force constants a little bit. What information do we get from force constants? It can tell us a little bit about the bonding in a molecule. So the single bonds have a smaller force constant than double or triple bonds. So for fluorine, difluorine, the force constant's around 500, 470 newtons per meter. And so that's typical for a single bond. So about 500 newtons per meter would be a single bond. It looks like 1,200 or so is for a double bond. So O2 has a double bond. And then nitrogen has a triple bond. It's about 2,300 would be a triple bond. And then you have carbon monoxide. And so you can write the Lewis-Dot formula for carbon monoxide, and you can make a triple bonded carbon monoxide, or you can make a double bonded carbon monoxide. And one reduces the formal charge, the other gives you the octet rule. So it's kind of, which one is it, right? And then you look at the force constant and say, well, which one is it? It's much higher than a double bond, but not quite as strong as a triple bond. So carbon monoxide is a strange molecule. I'll just leave it at that. Now, thinking about the units, you will see in the literature different kind of units for force constants. Sometimes you'll see newtons per meter, but other times you'll see dynes per centimeter. And you may be wondering, what on earth is a dyne? There's two types of metric systems, two base units, two different systems. Okay? One is the meter kilogram second, or MKS system, and that's the one we use the most. Okay? But there's also CGS. And so if you know MKS stands for meter kilogram second, then you can probably figure out what CGS, centimeter gram second. And so a centimeter gram second system of units would give you the dynes. So a dyne is the same thing as a force, as a newton, but with different units. So it's a gram centimeter per second squared. What is a force? Well, this should be the most basic physics formula that you remember. What is F? MA. F equals MA. So if Newton is a force and a dyne is a force, you know you have to have a mass and you have to have acceleration. So mass is either kilogram or gram, and acceleration is either meters per second squared or centimeters per second squared. So it's very easy. If you go back to the beginning, F equals MA, you can figure out what these different units are. What about a joule? That's work. Well, work is lifting a mass against a force, a certain distance. Okay, so the force is a newton, so you've got mass times acceleration, and you lift it a certain distance, you get another distance. So a joule is a kilogram meter squared per second squared. What would you think the unit for energy would be in a CGS system? It would be a gram centimeter squared per second squared. And do you know what the term for that is? It's not a joule. It's an erg. ERG. Okay? But we use this all the time. You ever heard of ergonomics? That's where that comes from. Okay, so thinking about the energy it takes to sit at your desk and click your mouse, you know, that's about an erg, is one mouse click. But anyway, the erg is the CGS energy. Okay. We use that also in thermodynamics. When we talk about exothermic for heat, what about delta G? If it has a negative delta G, we say it's spontaneous. We also say it's exergonic. And so now that erg is in the middle, so it's giving off energy. It's exergonic or endergonic. Now let's look at, if you're given a table with dynes per centimeter and you want to convert that to newtons per meter or vice versa, then I've got this whole unit analysis. So Newton per meter is, and converting that all the way over to dynes per square centimeter, all these things cancel out, and you end up with a Newton per meter is 10 to the 3. The only thing that didn't cancel, a dyne per centimeter. So it's 10 to the 3 dynes per centimeter, or a millinewton per meter is a dyne per centimeter. So this is a helpful conversion when you're looking up force constants in tables, or using the force constants out of Gaussian. Let's talk about transitions. So the 0 to 1 is the fundamental transition. And next week's lab, I'm trying to think, we won't. There are some peaks in benzene that are not fundamentals, but we won't be identifying any of them. Okay. So next week's lab for chlorobenzene and for benzene, everything that we identify will be a fundamental. And so you'll see lots of peaks in the spectrum, but they're all fundamentals. They're all the 0 to 1 for a different vibrational mode. How many vibrational modes does benzene have? 12 atoms. 12 times 3 is 36. Minus 6 is 30. Okay. Now, 30 vibrational modes. We'll see in the table in here, there's really only 20 frequencies because 10 of those are doubly degenerate. So you get 20 out of 10 vibrational frequencies. So there should be 20 peaks in that spectrum if everything was IR active and everything absorbed between 400 and 4,000. So we have 20 individual peaks for benzene's motions. And they're all fundamentals. Okay, so I want to try to get you out of the particle in a box now, where you just had one possible motion, one possible excitation. Now we have benzene, 30 motions, 20 different vibrational frequencies, all fundamentals. Okay? Because you can have this motion go from 0 to 1. Okay? You can have this motion go from 0 to 1. So every one of those motions can go from 0 to 1 and have a fundamental frequency transition. You can calculate the transition energy. So you have from 0 to 1. It's pretty simple. It ends up basically canceling the vibrational quantum number part. So this reduces to just 1, and so you just have the vibrational frequency. Now the HC converts it to joules, since we're talking about joules, but you could just talk about wave numbers as well. So the vibrational frequency is also the difference in the energy levels. And so that absorption shows up at the vibrational frequency value. Now, 1 to 2 is a hot band because it's excited into 1. 2 to 3 would be a hot band. 3 to 4 would be a hot band. Anharmonicity allows the plus or minus 2s and plus or minus 4s. So you do have overtones. A lot of times these overtones show up in the near infrared. So they're not in the infrared spectrum, they're in the near infrared, closer to the visible. The 0 to 2 is the first overtone, and 0 to 3 is the second overtone. So these are slightly different than the particle in a box. You guys were great on that test. Most everybody nailed that page where I had the arrows and you were looking at the different transitions, and so you know what your first overtones are and so on. But I hope you know it conceptually and not just memorized. Because if you've memorized first overtone is always 1 to 3 or 1 to 4, and then you're going to be wrong when it comes to vibrational motion. You need to think of the first overtone being skipping levels. Okay, so overtones skip levels, and what's the smallest skip level is 0 to 2 in a vibration, and the next smallest is 0 to 3, so that'd be the second overtone. And so then the first overtone frequency, then you can put in It's basically twice the vibrational frequency. But because this is allowed by anharmonicity, you have the anharmonicity constant in there. So in terms of larger molecules, polyatomics, you can do infrared spectroscopy on solid, liquid, and gas. Only, write this down, only gas shows rotational levels. It's a little foreshadowing to the next lab. We can have rotation and vibration show up in the same spectrum, but only for a gas sample. Liquids and solids, you're just seeing vibrational transitions. IR is very sensitive, so if your sample's too thick, it'll be opaque. You won't get any light through. Raman has trouble, we'll get in the Raman next time, with colored samples, because if you're using a visible laser and it gets absorbed by the sample, it's going to heat up and burn. So you can set your samples on fire with the Raman laser, which really was a big hazard when I worked with explosives. So you don't just walk up to a large explosive and shoot a laser at it and live to tell about it. Yeah. So we get powdered samples and put that on a small coupon and look at it, and you're trying to take a spectrum, and then you see a wisp of smoke, and you're like, the sample's gone. You know. So yeah. So sometimes they spin the sample so that you're only touching the molecules with the light very quickly. You know. So anyway. So the rotational structure is not resolved in liquids, solutions, or solids, but you can in a gas. And then because Raman and IR measure the vibrational motion of a molecule, they're great companion techniques. And so Raman has come down in price because of the advent of lasers, now especially with diode lasers. And so especially in forensics, you're seeing outfits that have an IR and a Raman, so they can get spectra from both. This is a spectrum that we're going to analyze, the automobile exhaust. And we see carbon monoxide, we see water, and we also have carbon dioxide and carbon monoxide. And then later on, we're going to talk about what these are. These are combination bands. So this will be sometime next week, like next week, we talk about that. So we see the asymmetric stretch in CO2, we see the bend in CO2, but we do not see the Raman active mode, the symmetric stretch for CO2. So it's at 1380, and we're hitting that molecule with light that has got 1380 wave numbers, and it's not absorbing it, even though there's a stretch that could absorb it, but symmetry selection rules disallow it. And that shows up in Raman. Now, notice this notation, 0, 1, 0, and 1, 0, 0, and 0, 0, 1. This x-axis is wave numbers, and that is the difference in the energy equations. This is the Schrodinger equation. You recognize that. And so we have, and forgive me, but this is history here. The double primes are the lower states. And the primes are the upper states. It seems totally backwards. Go ahead and get that in your mind, because for the iodine lab later on, you're going to get everything's double prime and prime. So I think the reason this happened is the first spectroscopic measurements were all emission. And so the initial state was the prime, but it was the upper state. And the final state was double prime, and it was the lower state. But they just kept it. Lower state was double prime, and single prime was upper state. So if we have this difference, and they're all fundamentals, notice that we have 0, 0, 0 here, and then the upper vibrational states here and here. And so all we really need to do to label a peak, since half the information is all 0, 0, 0, these are fundamental transitions, is just label that peak with the vibrational quantum numbers in the upper state. Okay. And so CO2 has 4 vibrations, because it's 3n minus 5, but 2 of those motions, this bending motion, is symmetric. So it's the same, it's degenerate, it's the same energy, whether it bends in the x direction or bends in the y direction. It's the same energy. So we really only have 3 peaks that we're going to see, either in the infrared or in the Raman. And so we label those with their quantum numbers. And so this right here would be nu2, because the change is in the second quantum number. This is, I think, nu 1, yeah. And this is nu 3. That's another way to label them. But I want to put the 3 numbers in parentheses just to show you that we've gone from 0, 0, 0 to 0, 0, 1, or from 0, 0, 0 to 1, 0, 0. So only one of those motions is excited. Over here on the combination bands, we have multiple changes at once, and we'll hold that off for a little bit. Any questions about this? This is the spectrum, and these are spectral lines. Let's look at the energy levels. So these are the energy levels. So this A1G, A1U, and the D-infinity age character table, we have the infrared mode, which was the asymmetric stretch, which the motion is shown at the top, nu 3. So 2350 wave numbers, and that's the one shown in red there, the infrared active. The Raman active, 1388 wave numbers, okay, is a 2-photon technique. We have the green laser coming in. It's oscillating the electron cloud, but not being absorbed. That's what that dashed line at the top is. That's a virtual state. So this is not an absorption level up here. It's scattering off a red-shifted photon. So yellow light comes out, and the difference is this Raman active mode. So the difference between the incident and the scattered light is 1388 wave numbers. And so that shows up right in this middle infrared range. So we could overlay a Raman spectrum and an infrared spectrum. And where the Raman peaks are, you'd see the transitions in the Raman, and where the IR transitions are, you'd see them in the infrared. And that's what you'll do next week with benzene and chlorobenzene. We've looked at the water normal modes. Let's just go through all of the different vibrations in a molecule. Here is acetonitrile. So it has 1, 2, 3, 4, 5, 6 atoms. Times 3 is 18. Minus 6 is 12. So 12 vibrations, and that was one of the test questions last time. And so you have 12 vibrations, but I only see 8 here. And that's because 4 of them are doubly degenerate. Okay. So we have 8 frequencies, but these down here are doubly degenerate, so they count twice. And we'll see how that works in the spectrum. So let's go through the spectrum. We do have some, so the really low frequency modes are the bending modes. Okay. And again, what makes the frequency high or low? Think about that equation. Frequency is equal to the square root of the force constant divided by the reduced mass. So if we're moving a lot of mass, then you got a low frequency. So if bending the whole molecule, you're moving a lot of mass. And the K is the force constant. That's how tight the spring is. Well, it's really easy to bend a spring, very difficult to stretch a spring. So bending modes have really low spring constants. And so again, low frequencies. So way down there to the right of this spectrum is the bending mode. And there's both motions in the X and the Y direction. Then we have the carbon-carbon stretch. So that's nu 4. It's along the Z-axis, and so it's an A1 mode. Then we have nu 7, which is, again, in X and Y directions, but it's the same frequency. So that shows up at the same peak. Okay. Then nu 3 is the symmetric angle or bend of those hydrogens. So the carbon-hydrogen bond angle is changing. And all 3 angles are changing, either together, shrinking, or expanding together. So you can call that an umbrella mode because it looks like an umbrella. Like might flip out, invert itself. And then you have other angle bends, nu 6, and there's 2 of those again because it's doubly degenerate. Then you have the the nitrile stretch, so the triple bond stretch. So you're moving a nitrogen and a carbon, pretty light atoms, and then you've got a triple bond, a tight spring. So that's at 2200 wave numbers. Then we get into the CH stretches. We have the symmetric stretch and the asymmetric stretch. So that's all 12 motions for this molecule. And you see the higher frequency ones show up because they're moving smaller masses. The hydrogens are light, and even though it's a single bond and the carbon-nitrogen was a triple bond, Carbon nitrogen has a higher spring constant, but it's moving heavier masses. And the CH stretch, single bond, so it's fairly small K, but it's only moving a mass of 1. You can do the same thing with benzene on your own. This little website shown here will take you to a place where you see all of the benzene vibrational modes. And you can look at those, you can turn them around, you can see the ring deformations and so on. So that's vibrational motion. The main points for today were the equations, the energy equations, the vibrational frequency equation, the reduced mass, being able to calculate all of those things, and then looking at the spectrum and getting in your mind that like CH stretches are high frequency, moving carbon-carbon stretches are middle frequency, and then bending the whole molecule is really low frequency.